In the previous class, we discussed that when a wave is incident from a dielectric medium onto a conductor medium boundary, something very interesting happens. The phenomena is in some sense very similar to total internal reflection, but more than that, we are seeing that essentially when we are able to make waves incident on a conducting body and make it reflect, so some amount of energy essentially travels along the conducting boundary. So that is something very interesting. So in the previous class we had seen the case of vertically polarized waves, or that is a perpendicular polarization. We had seen that the incident wave has essentially three components. The incident wave has its electric field perpendicular to the plane of the paper. So the magnetic field would look like this. So essentially there are three components. The boundary is along the x-axis, the normal is the z, and the y-axis is perpendicular to the plane of the paper. So the electric field has a component Ey, while the magnetic field has a Hx and Hz component. So likewise for the reflected wave, something very similar. So what we saw was that if we are able to make multiple waves travel, so because of the interference of these waves, multiple or other in sets of incident and reflected waves kind of superimpose on each other. So because of that, we have something called as a total field, both E and H, in medium 1. So what essentially happens is that these components were denoted as some E1 and H1, and these have the same components as before: the EY component, the HX component, and the HZ component. We saw that when EY and HX are looked at, they have a phase difference of 90 degrees. Thereby, these two do not constitute any wave. But what happens is we looked at EY and HZ. So the EY component and the HZ component, essentially, they constitute a wave along the x-axis. So the EY and HZ create a wave traveling along the plus x-axis. So then what about HX? So HX with respect to the boundary is the tangential magnetic field. So that was non-zero at the boundary. What we saw was EY and HZ, they are both 0 at the boundary. We saw some other very interesting phenomena also, that EY and HZ kind of, and even HX for that matter, they kind of form standing wave like structures as a function of Z. So as a function of Z, there is no time variation whatsoever. So all of these constitute some kind of a standing field pattern. So what happens is HX is non-zero at the boundary. So this is the tangential magnetic field along the boundary. So as per our definition of boundary conditions, we know that a tangential magnetic field at a conductor boundary will create some surface current. So if you recall the expression that we had derived for the Hx, so Hx is the tangential H field at the boundary. So there must be some surface current which is generated. So this surface current Js vector is nothing but the normal vector on the surface, and in this case the normal vector is the Z times the Hx. So you know that Hx is aligned along the Z direction. Sorry, Hx is aligned along the X direction. So Z cross X would essentially give me a vector which is aligned along the Y direction. So essentially it would become Hx times Y. So Hx, which we had derived in the previous class, was something of this kind. 2ei0 by eta 1, where eta 1 is the characteristic impedance of the medium 1, cos theta I, so since we are solving at the surface, we must put z equal to 0. So if we put z equal to 0, let's write that down. So it was like this. Times e raised to minus j beta, where beta is the phase constant in the medium, beta x sine theta I. So at the boundary z becomes 0. So this cos term becomes 1. So put z equal to 0 at the boundary. So here we get 2ei0 by eta 1 cos theta I e raised to minus j beta x sine theta I y component. So this is what it looks like. So some surface current is induced along the y direction. So it's like saying you have this metallic boundary. Some surface current will flow towards y. So y, as you know, is like this. So the Js will look like this. They will also be aligned along y. Well, they can be aligned this way also, but really doesn't matter. What is important is that the surface current is aligned along the y-axis. So this is Z. So what we had seen was, because of the non-zero Hx at the boundary, you have a kind of standing wave pattern for the Hx like this. If you plot it as a function of Z, so this distance is essentially some form of lambda by 2. We had seen this in the last class. So I had ended the last class by saying that what would happen if I place one more metallic body at a distance of lambda by 2 from the original surface. So you will see, even if I place a metallic body, the field maxima is still happening over here. So there is absolutely no difference. Only thing is that further the field will not exist, but this kind of a pattern will be there. So we had seen that just like Hx, Ey and Hz also had some similar kind of a fashion. So we had said that if you look at, this is the boundary of the conductor, if you look at Ey and Hz, so Hz, EY and HZ, they look something of this kind, like this. They are both in phase. So I had said that just like the case of Hx, this is also some lambda by 2. So if I place one more conducting body or conducting surface over here at a distance of lambda by 2 from the original conductor boundary, it is essentially the same. So why am I saying this? What is the need for putting one more conductor over here? The need for putting one conductor over here is that when a wave hits the boundary, we saw that it creates some energy which goes over there. Now, can I keep this energy flowing? I can do that by making multiple reflections across two surfaces, and therefore some energy will flow here, 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 like this. So this is the way with which I can sort of guide some energy because of an electromagnetic wave, but along some conducting surface. And this is one way through which the energy or part of the energy of the wave can be channelized to make it go in the direction that I want. We shall be visiting this concept later. So now once we saw the wave along the plus x direction, so this sort of looks like some constant times e raised to minus j beta x sine theta. So this I can write in the form of a propagation constant as e raised to minus j beta sine theta times x. So therefore, the wave that is traveling along the plus x direction has a phase constant, let us call it phase constant of the wave along the plus x axis. Let's call it as some beta prime, and that is beta times sine theta I. So with this, the wave can be written in the form of e raised to minus j beta prime x. So this is the wave traveling across along the plus x direction, having a phase constant of beta prime. So if I want to characterize the wavelength of the wave, so I can define some lambda prime also, which is not equal to lambda, that is 2 pi by beta prime, which is 2 pi by beta sine theta I. But 2 pi by beta is the lambda of the original wave. So this is lambda by sine theta I. So this is the wavelength of the wave which is traveling along the plus x direction, if you say that way. Now, all of this we had discussed for the case when the incident wave was perpendicularly polarized or vertically polarized. Now let us very quickly, just take a recap and look at what happens in the case of the parallel polarization or horizontal polarization case. on a conductor boundary. So now this is what it would look like. The conductor, let us say this is x-axis, this will be the z-axis, and obviously this is y. So let's say the wave is incident with an angle of theta I. Because the E field vector is now on the hz plane, the H vector will now be like this. So this is Hi, and therefore the electric field vector Ei will exist like this, and this is the reflected wave. So HR would also stay the same way, vertical, and the electric field would look like this, ER. So now again I will not write each of the field equations. By now I am sure you know how to do that. So please go ahead and do that. So that part is left as an exercise to the reader or to you. So what can we say? Just like how we had derived the reflection coefficient for the case of the perpendicular polarization, we can also define the gamma or the reflection coefficient at the boundary. That is ER0 by EI0. This is 1. So you have to prove this. I shall not prove this for you. You have to prove this yourself. So this is very similar to the case of open circuit load on a transmission line, that you can say just by looking at the gamma. So now again let us suppose we have made incident multiple waves and there are multiple reflections which are parallel to each other. So again I can define something called as a total electric field in medium 1. So I am writing the answer directly. I am not proving the whole thing. You can continue from the proof of this. So in this case, E1 vector is now notice that the E field is on the xz component or in the xz plane. So E1 will have two components, one x component and a z component. So let's write this down. Sine of beta z cos theta I, x component minus 2 ei0 sine theta I cos of beta z cos theta I, z component, this whole into e raised to minus j beta x sine theta I. So just like the previous case, here also this field seems to be part of a wave which is traveling along the x direction. So let us write the total H field now. So H field will be much simpler. So this you will get as H1 is 2ei0 by eta 1 cos of beta z cos theta I times e raised to minus j beta x sin theta I, but on the y component. So in this case, we have three components of the total field. We have hy, ex and ez. We have hy, ex and ez. Again, you can do a similar analysis what we did for the perpendicular polarization case. You can examine each of these components and you can prove something. Here you can prove something also. So what can we prove? So let's write this down. So hy is 2ei0 by eta 1 cos of beta z cos theta I, or let's call this as sum k1 cos beta z cos theta I. Ex, the magnitude part, I can write as sum k2 sin of beta z cos theta I, and Ez will be sum k3 cos of beta z cos theta I, just by looking at the expressions that we have derived or we have written. The derivation is left to you as the exercise. So again, if you look at the boundary, this is the x-axis, this is the minus z-axis. So if I now draw the three components hy, it will look like this. It's a cos term, so something of this kind. Ex, this is hy. If you draw ex, it is a sine as a function of z, so it will be something of this kind. And Ez will also be a cos, so just like hy. Something of this kind. So what we see is Ex and Hy can never constitute any power flow because they are out of phase. But Ez and Hy constitute a power flow in the x direction. So Ex is the tangential field on the boundary and that is 0. So there is no concept of any surface charges at all. So then what can we say? Which component can cause some surface charges or surface current? So the Ez component exists along the z direction. So this is the normal component of the field on the boundary, and this will give rise to surface charges. And Hy is the tangential magnetic field which will make those surface charges move as surface current. So effectively Ez and Hy constitute a wave moving along plus x. So this is the very similar way with which we can analyze, just very similar to the case of the vertically polarized incident wave. So again, what we are seeing is that these wave or field patterns are kind of repeating. So I can say that what if I place one more conductor over here? So it's like the nature is preserved. So what was maximum over here is maximum over here also. So again, the concept of, or the motivation to place another structure over here is whether I can make a wave incident multiple times and sort of create this energy propagation along the plus x direction, because we are seeing that one incident wave is causing some energy to flow in the x direction. So can we improve upon this by having two conductors and multiple reflections, which can actually help us sort of make the energy flow along the x direction. So that is called as a guiding wave structure. So why we want to do this? Why do we want to do this? When a wave is generated, an electromagnetic wave is generated, it can be generated by different means. It can be generated by means of a circuit. It can be generated from a source which is far away from the circuit with which we are working. In that case, suppose we want to receive a wave from some source which is far away, and there is no wired connection between my circuit and the wave which is being transmitted from that source. So how do I catch that wave? So suppose the source is transmitting some waves via some antenna. So as you know, an antenna is a device which sort of converts a circuit wave into wireless energy. And suppose my receiver also has an antenna which is trying to capture that energy. So that way it will be a very good idea if the wave is made to be guided along a structure. So the way we are receiving the wave, we are not sure what kind of angle it is making. So therefore, if we have a guiding structure like this, we can sort of make the wave travel in the direction that we want. So let's write this down. So the structures using conductors or whatever to guide a wave along some desired direction is called as a waveguide or guiding wave structure. Now, you might say that, you might ask, can you take some examples of waveguides? Yes, we can. The simplest example of a waveguide is a pair of conductors or a pair of wires. You have used probes with oscilloscopes, and those probes are essentially nothing but coaxial conductors. You have an outer conductor which encloses an inner conductor. So this two conductor system is also a waveguide, and these two conductors are placed in a very strategic way through which they can guide the wave which is coming over here, the fields rather. The field components of the waves will be guided through and the wave energy will propagate. This is an example of something called as a coaxial cable. Another example is copper lines on a circuit board. So you have, let us say, a circuit board which is made of a dielectric, but on this I am making a copper patch, a copper line, and on the bottom also I am making some copper connection. So this is an example of a two conductor transmission line or a waveguide. So even a transmission line in some sense is guiding a wave. So this is called as a microstrip line. There are optical fibers also which work with just a single element. There is no conducting element over there. There are hollow tubes also which work with single conductors, but we shall see that later. So our motivation in the previous discussion so far was that can we use two metallic conductors? We saw yes, if we put two metallic conductors which are separated by some particular distance, we can indeed repeat the fields and therefore expect some energy to flow. So the simplest example of a waveguide is a two conductor system. A two conductor system separated by a dielectric. That is the easiest example. Now let us revisit our case of the vertical polarization. That is when the incident wave is hitting some conducting boundary and the E field of that incident wave is vertically polarized. We are going to revisit this but with a slightly different change in perspective. Let us redefine our axis. Let us now draw the conductor horizontally and call this as the Z axis. Let Y axis be like before, which is perpendicular to the plane of the paper. So Y axis is coming like this. So that means where will be X axis? Again use the right hand thumb rule. X axis will be like this. This is plus X. So now suppose a wave is incident like this. It will be reflected. Let's now call this as theta and theta. There is no need to call I anymore because there is no transmission. There is no transmitted wave rather. And the electric field vector is vertically polarized. So therefore the H field will look like this. So in the reflected wave also the ER will look like this and the HR will be in this direction. Is that fine? So once we have this, what can we say? What can we say? We can say that if you look at the total field, so this is conductor I should say, and this is dielectric. So total field in the dielectric, so means both E and H fields, they consist of three components. The E component, which is vertical, that is along the y direction, so that is EY, and H, which is lying on the xz plane, so HX and HZ. So what we had said was that if the wave is incident on the boundary, there is some propagation which happens along the plus z direction. Earlier discussion it was plus x, now it is plus z. So therefore, if you rewrite this, I can say that EY and HX constitute a wave flowing towards plus z direction. Yes, and HZ does nothing, no wave, just creates, what does it create? HZ is the tangential field, so it creates the surface current. So what we had seen in the previous class in the discussion of vertical polarization, we had essentially written these fields as a function of z. So let's write that down again. So there are three components now: EY, HX and HZ. So the yes, so we had said that let these be some form of this kind. Let's say this is some K1 sine of cos, I'm sorry, K1 sine of beta x cos theta, because now we in the previous class or in the previous discussion we had written these fields as a function of the z direction, but now since we want to write these fields as a function of the normal to the plane, we will write as functions of x, so something of this kind. So this is the way. Hx would be some K2 sine beta x cos theta, and Hz is K3 but cos beta x cos theta. Remember that Hz is out of phase with Ey and also Hx. So I mean, again we had seen that some kind of a standing field pattern is created. So this is the surface for the Ey and Hx. So now let us say this is the x-axis, this is the z-axis, and this is the y. So when does Ey become 0? So we had said Ey becomes 0 at certain points along x. So let us say that some distance from the boundary, let us call this distance x equals d, some d. At some distance d from the boundary, that is, let us say here, it can be this one also, let's say this is d, the distance from the boundary at which the EY field becomes 0. So when would that become 0? When the argument of this sign becomes equal to some multiple of pi. So the argument, so when I substitute x as d, I will get beta d cos theta. Cos theta will be equal to some m pi. Now since x is positive, I can say m is the set of the natural numbers. It can be 1, 2, 3, 4, whatever. So beta, now what is beta? Beta is the phase constant of the wave that is originally incident. Beta is the phase constant of the wave that is originally incident. So we had defined something called as beta prime also. This is not that beta. So beta and beta prime are different. So here beta I can say is 2 pi by lambda times d cos theta equals m pi. So I can remove the pi and I can say that d is equal to m lambda by 2 cos theta. So what I am saying? I am saying that at every distance of some multiple of lambda by 2 times some constant, it's not exactly lambda by 2, but there is some implicit connection of lambda by 2, and at every integral multiple of this quantity, the electric field will die down to 0. It's a repetitive procedure. So what can I say? So suppose I am writing it this way now. This is the z direction, this is the x direction. Sorry, x. So if I now write, let us say m becomes equal to 1. If m becomes equal to 1, I will get something like this. This is the first d. So it's like saying, if I place another conducting body over here, it makes absolutely no difference, because whatever is the boundary condition for the first conductor, the same is getting satisfied for the second conductor also. And that is true for all the fields, not just EY. So EY will look like this. So this is something very interesting. EY looks like this, even HX looks like this, yes. And the HZ kind of looks like this. There is a maxima over here, and somewhere later the minima will come, and then again a maxima. So this is EY, this is HX, and this is H of Z. So now we have two conductors which are parallel to each other and separated by a distance d, where d is equal to lambda by 2 cos theta. I have put m as 1, so therefore d will be equal to lambda by 2 cos theta. And this is what we have essentially proved and seen its practical implication this way. So now let us not lose track of what we are doing, or let's not lose track of what we started with. We started with the bottom conductor. We started with the bottom conductor. This is the Z direction. This is the X, and this is Y. So we had said that in case of perpendicular polarization, let the wave be incident this way and reflected this way. So the electric field was perpendicular to the exact plane, so that's why it is along the y-axis. Now what we had proved earlier was that some wave is flowing along the z direction. Now when this reflected wave hits the second boundary, a similar phenomena happens and some energy propagation is created in this direction again. So this is the way with which multiple reflections can guide the energy along the two surfaces. So these two are called, the structure where you have two metallic or two conductive plates which are kept parallel to each other to guide a wave. This is called as a parallel plate waveguide. So, and this perpendicular polarization, where you can see the direction of the E vector is perpendicular to the plane of the paper, while the direction of the flow of the induced wave, so to speak, is along this Z direction. Remember, the main wave is still there, but the power being contributed, or the contributed power which is being guided, is because of the induced fields. So these are something like induced waves. So while the direction of power flow is along the Z direction, the electric field is perpendicular to the axis over which the power is flowing. So this kind of propagation is called as a transverse electric or TE propagation. Just to repeat, transverse electric means the electric field vector is perpendicular to the direction of propagation. Notice now I am not talking anymore about the individual waves. Those are still transverse electromagnetic. But I am talking of the field with respect to the direction of propagation of the flow of power or energy, that is the energy or the power that we are guiding. Okay, so as we had proved, we had taken, let us say, m equals 1, for example. D is lambda by 2 cos theta. So now the general case where we had said the general case is which we had written earlier, that D equals m lambda by 2 cos theta, where m can be any positive integer or a natural number. So D is m lambda by 2 cos theta. We had looked at a special case of m equal to 1, but something similar will happen for other values of m also. So if I want to write cos theta, where theta is the angle of incidence, so cos theta is nothing but m lambda by 2d. So if I now introduce that beta x term, what I will get is beta x cos theta is again beta x times m lambda by 2d, and this I can write as 2 pi by lambda, x I'll put over here, m lambda by 2d. So lambda and lambda will cancel and this will cancel. So what we get is m pi x by d. So now this is a fairly useful form of representation. Why? Because now once we have introduced those two metallic plates, it is often very difficult to know inside what is the value of theta. So therefore, representing these cos and sine terms without using theta has its own advantage. So what is the phase constant? So phase constant, the phase constant of what? Of the wave along plus z. That is the wave through which we are guiding the power. So that is, we had proved it is beta times sine theta. So that is nothing but 2 pi by lambda times sine theta. We already know cos theta, so we can find out sine theta as 1 minus cos square theta, or this 1 minus m lambda by 2d square. Yes. So this is what is the phase constant. Now, depending on what is m, I can have the plates for m equal to 1, the plates were like this. For m equal to 2, the plates will be like this. M equal to 3, the plates will be even more further apart. So whatever you want to say. So whenever we normally say that this is the transverse electric mode of propagation, we also mention a suffix as the small m, where m is called the mode or the mode number. The mode of propagation is transverse electric, and small m in the suffix denotes the mode number. So in case of the TE mode was because of the perpendicular polarization of the wave which was incident. So from now on, we will not use this word perpendicular polarization at all. So we'll understand that TE is essentially perpendicular polarization, but we will not call it this. We will just say the fields, or we will just use that name TE. Okay. So now we know that in this case, in the TE mode, when the wave or the field is essentially perpendicular to the plane of the paper, the electric field, there are three components: EY, HX and HZ. This we have proved. So now let us write them what they are. So EY is minus 2J EI0 by eta, where now eta is the impedance or intrinsic impedance of the dielectric. So this times sine of beta x cos theta times e raised to minus j beta beta z sine theta. Yes, because z is now the direction of propagation of the wave constituted by Ey. So Hx is minus 2j Ei0. Oops, sorry, there will be no eta over here. The eta will come over here. Sine theta sine of beta x cos theta e raised to minus j beta z sine theta. And likewise for hz. So hz I am not writing. So now all of these expressions are functions of theta. So we were just saying a few minutes back that always it is not possible to know what is the theta inside the waveguide, inside the parallel plate of conductors. So is there any way through which we can eliminate this? So I can rewrite the Ey this way: minus 2j Ei0 sine of, we had already derived what is beta x cos theta. So beta x cos theta is this quantity. So sine of m pi by d times x times e raised to minus j. Now beta sine theta, we had already derived this as the phase constant. So this is minus j beta z 1 minus m lambda by 2d the whole square. This is the electric field on the y component. So you can also put the y vector. But suppose you don't put that, then this is the way. So you can write even without y in that case. So likewise hx will be what? It will be minus 2j Ei0 by eta. Now sine theta is this. Times sine of this quantity times e raised to minus j beta z times 1 minus m lambda by 2d the whole square. This will be along the x-axis. And likewise for the hz, you can write that yourself. I am not writing it. So you can see that we are writing the fields without using theta. So this is a very useful approach and which will help us a lot in our analysis. So now, after looking at all of these big expressions, let us try to understand some of the fine print with these waveguides. So now what we are seeing is we are able to generate some power flow along the surface of incidence when we make some wave incident on it. Now suppose you have just one conductor, then whatever angle you make the wave incident with, it is probably bound to give you some wave which is traveling along the conductor, meaning as long as the sine or cos terms don't become zero, you should be safe. But now we don't have just a single conductor, we have two conductors. We have two conductors, and the problem now is that the theta or the angle of incidence need not be now anywhere. So it's like saying I have these two metallic plates which are separated by distance d. So now the question is, we had said that we had introduced this metal, the second metallic surface, at the exact place where the boundary condition is being satisfied, similar to the first conductor. But now suppose I ask the reverse question. Now if I ask the opposite question, suppose I already have two plates which are separated by a distance d. What should be the constraint on the incident wave on either surface such that the boundary conditions on both fields or on both surfaces are satisfied? Fair enough? Our analysis so far was that we had started off with one surface, and then we had analyzed how the fields are behaving along the x direction, and then we had sort of introduced one more plate, conductor plate, at the point at which the boundary conditions were again being satisfied, similar to the first conductor. But now the question is, somebody gives you a parallel plate waveguide structure already. Now you cannot play with D. Once you have the parallel plate waveguide, you cannot play with D. It is fixed. It's done. So now the onus is on the wave. The question now is, will there be any constraints on the wave that is incident over here which will still satisfy the boundary condition at both plates properly and still cause the wave propagation on both surfaces? So let us say this D, so D normally is m lambda by 2 cos theta, right? So from this we have to say that D is in such a way, or D should be in such a way, that boundary conditions should be satisfied on both plates. So to satisfy boundary condition on both plates, what is the condition? We had written it down. So the condition is this: beta d cos theta should be equal to m pi. So this is what should be there. Now let's say by putting this boundary condition, we get this. So now let's suppose m is 1. Let's take the special case. So in that case, D will be lambda by 2 cos theta. D will be lambda by 2 cos theta. Now let's say that D is less than lambda by 2. D is less than lambda by 2. If this is the case, That means if d is less than lambda by 2, then cos theta has to be definitely more than 1, which is not possible. So that means if I put d as lambda by 2, that is the minimum possible separation, I will get cos theta as 1. I will get cos theta as 1. So in that case, theta is 0. So it's like something like, normal incidence. So now this is a very strange thing. But suppose we say that d is lambda by 2, that means theta is 0. That means the wave has to be incident this way. So it's like saying the waves will keep hitting the two plates back and forth, nothing will travel anywhere. So you can very easily prove that the moment theta becomes 0, the propagation constant of the wave this way or this way also becomes 0, because it is a sine theta term. So this puts us in a bit of a dilemma. So this means that we should put d as more than lambda by 2. But what did we start with? We started with saying that d is fixed. So we don't know what d is with respect to the wavelength of the wave. And this is what we want. The moment d becomes more than lambda by 2, theta will be some angle which is between 0 and pi by 2. And that is what we want. So now again we are in a bit of a spot of bother. We don't know what is d. We don't know what is d. But if I know, or so let's say d is fixed. Let's say d is fixed and the wave which I want to propagate, I cannot change its lambda. Okay? So in that case, what we want? We can only change theta. So cos theta is lambda by 2d. So for theta to be between 0 and pi by 2, this lambda by 2d should be less than 1. So that means what? If you solve this inequality, again you will get d is more than lambda by 2. And that is okay. So what I am saying is, by changing theta between 0 and pi by 2, I can increase the number of solutions. How? Now let us put m back again. So we had said that in general d is m lambda by 2 cos theta. So again if I take theta on this side, I will get cos theta is m lambda by 2d. So we saw that if m equal to 1, so we need d more than lambda by 2, and this means 0 less than theta less than pi by 2. So suppose if I have m equals 2, what will happen? So to have cos theta less than 1, d should be more than lambda or something of that kind. So now the thing is, let us say d is fixed and lambda is also fixed. So let's fix d and lambda. By doing this, what I can say is that cos theta becomes m times lambda by d. Okay? So let's call this as some constant k. So for m equal to 1, what is theta? So for m equal to 1, theta is cos inverse of k by 2. For m equal to 2, theta becomes cos inverse of k. So by choosing our theta properly, or you can see that for different values of m, there are different values of theta with which the same wave may be launched. So we can try to ensure that the value of m, so let's take theta 1 and theta 2. So definitely theta 1 and theta 2 need not be the same. So what I'm trying to say is that for different values of m, we have different values of theta. And theta is nothing but the angle with which the wave is launched into the waveguide. So the point is that this m is kind of our trump card. The m is kind of like our trump card, because for different values of m, there exist different values of theta through which we can launch the same wave and still make it propagate. So I can say different values of m give us different theta with which the wave can, or which the same wave can be launched. Why same wave? Because we have fixed lambda. So if you now look at the field expression, which we had derived, yes, this one, the field expressions in terms of m. So if you look at, let us say, Ey. So if I am looking at this term, sine of m pi x by d, so what it is indicating? So let us say the Ey term, sine of m pi by d times x. So depending on m, if this is the x direction, I can have, let us say, this is m equal to 1 if the distance is d. So because if x becomes equal to d and m is 1, sine of pi will be 0. Now let us put m equal to 2. What it will look like? So if m equals 2, then there are two solutions possible, x d by 2 and at d. So it's something of this kind. This is what it looks like. This is where the second conductor is. This is the first conductor. Again, let us go for m equal to 3. So we'll now have 3 pi by d x. So what will now happen? The sine wave will look something of this kind. So it will go to 0 at d by 3 and 2d by 3. So this is d by 2, this is d by 3, 2d by 3 and d. The field will essentially have 3 minima, 1, 2 and 3. So it is interesting to note that the number m is actually telling us how many half cycles of the field variation are existing. So m is number of half cycles of the standing field. It's standing, we proved this, between the two plates. This is a very important result. So if somebody tells you this wave is traveling in some mode, let us say Te suffix m, you will know that acha, this m indicates how many half cycles of the field are essentially there between the two conductors. So that way you can have any number of half cycles. So now with this, let us try to understand the constraints in little more detail. So we said that for different values of m, there can be different values of theta. So what we want that always we want cos theta should be less than or equal to 1. Or generally it should be less than 1, not just equal to. So this we had proved, otherwise it will be normal incidence and nothing will happen. So cos theta is nothing but m lambda by 2d, and this should be less than 1. So now let us ask, what is the constraint on the wavelength of the wave which we can make it pass for TE? For TE mode, this is the requirement, that the cos theta should be less than 1. So if I now put lambda on the left hand side, I will get lambda is 2d by m. That means my lambda of the wave which is lodged into the waveguide should definitely be below this value. So I can say that lambda is nothing but velocity by frequency. This should be less than 2d by m. So that means my frequency should be more than mv by 2d. That means now if I have control over the frequency of the wave, I should always ensure that the frequency of the wave is more than this value. So therefore, because anything below this frequency, let's call this as f min, the minimum frequency is mv by 2d. So anything below f min, so if f becomes less than f min, no propagation inside the waveguide. So therefore this is called as the cutoff frequency. So it is kind of like a high pass filter. The waveguide sort of acts like a high pass filter in the TE mode, or let us say TEM mode, T suffix m. Okay, where if the frequency of the signal is below a certain limit, then the wave essentially cannot propagate, because the boundary conditions will not be satisfied. Cos theta will be more than 1, and therefore nothing will happen essentially. So now what? So for the wave that is propagating, along the plus z direction, so this is the waveguide. So the wave which is propagating along plus z, the phase constant, let us call it as beta prime, that is nothing but beta sine theta. So which we had already proved is beta times 1 minus m lambda by 2d the whole square. So what we can say is that if the lambda, so we had said that the lambda maximum is 2d by m. In the previous page we had said this, lambda should be less than 2d by m. So lambda max is 2d by m. So if lambda becomes more than lambda max, what happens? This term essentially becomes more than 1 and the beta becomes imaginary. So this means no propagation of energy. So therefore we looked at two things. One is the maximum wavelength, the other is the minimum frequency, which is also called as the cutoff frequency. So in today's class we saw how the concept of reflection from a metallic surface can be harnessed into a waveguide by having two surfaces which are strategically kept apart by a certain distance. So we saw what is the meaning of transverse electric propagation. That is nothing but the case when the wave that is incident on the first surface is perpendicularly polarized. So this presents us with an interesting concept through which we can guide energy along the metallic boundaries. Thank you.